down a little bit besides his busy schedule. So over to you, Larry, now.
Okay, thanks. You know, I should ask before we get started, does this class end at 2:50?
250.
2:50?
Yes.
Okay, good. So I'm going to talk a little bit today about using a computer algebra system in data analysis. Some of you know of this as Apple if you've taken Math 401 with me. What I decided to do was, this is a talk that could go on for hours and hours, and we'll end it right at 2:50. But what I'm going to do is I came across, let me show you the outline here. There are examples, and I'm going to show you just 2 examples, and then of all of these applications, I picked off 4 of the applications that I thought might be of interest with respect to people doing data analysis and probability modeling. So let me start with an example. Let's say you were given this problem right here, and that is x and y are independent random variables, and x has the triangular distribution. And I assume, how many here have had either Math 401 or Math 351? Okay, almost all of you. A couple of you haven't, but the triangular distribution, if you haven't seen it before, has a probability density function. It just follows the name. There is a triangular 1, 2, 4 distribution where 1's the minimum, 2's the mode, 4's the maximum. Okay? So the interest here is if x has the triangular distribution with parameters 1, 2, and 4, y has the triangular distribution with parameters 1, 2, and 3. What is the distribution of their product? Now, this is not the kind of question you would want to put in a Math 401 class unless you were trying to decrease enrollments, okay? It doesn't look too bad, but I'll show you what I would do if I were doing this by hand. This would annoy anyone who tried to work it. So the first thing that I'd do is I would draw an axis with x along here and y along here, and I would put breakpoints at 1, 2, and 4 for this x, and for this y I'd put breaks at 1, 2, and 3. And then what I'd do is I would draw in the hyperbolas corresponding to every single point that's along there. Okay? So now I know if I look between these hyperbolas, I've got 1, 2, 3, 4, 5, 6 sets of double integrals. Sometimes you've got to add those double integrals together to get the probability density function of V. Now here is how this particular problem is done in Apple. You say x is equal to triangular RV 1, 2, and 4, and it will store that probability distribution that I put on the chalkboard internally inside of Apple, which is a Maple-based language. By the way, Apple stands for a probability programming language. So it manipulates random variables. Then the second thing you do is you'd say y is another triangular random variable with slightly different parameters. And then v is equal to the product of x and y. And following that, you would come back, and there are the 7 different pieces, or I guess 6, 1, 2, 3, 4, 5, 6 different pieces. And in here is all kinds of stuff. I'm sure there's integration by parts and all this, but Maple does it all, okay? And it does it, less than a second. This is going to come back with it. So this is a nice tool for things like products or sums of random variables and this type of thing. There's one example, and that involves a continuous random variable. Let me give you another example. This involves a discrete random variable. There is a bag containing 15 billiard balls numbered 1 through 15, and for those who had me last semester in 401, I'm sorry, you've seen this type of thing over and over and over again. If 7 balls are drawn from the bag at random, find the probability that the median number drawn is equal to 5 when A, sampling is performed without replacement, and B, sampling is performed with replacement. So here's the Apple code just to give you a feel for part A. You would say x is a discrete random variable from 1 through 15. So equally likely to pick any of the balls out of the bag. And then there is a routine called order stat, and this was written by Diane Evans, who was a former William & Mary student. And what order stat does is it says, I am going to take 7 values from this population distribution, all equally likely, and I'm going to look at the fourth. Why the fourth? Fourth ordered value because you're looking at the median, right? And I'm going to sample without replacement, and I'm going to put that random variable into y. And then finally, my question here asks, what's the probability that y is equal to 5? So that's I call that the PDF of y, evaluated at 5. And there's the answer, 32 over 429. Now, the only change that's going to happen for part B is we're going to sample with replacement. So in this case, the code looks exactly the same, except there's not a quote WO that's in there. Same code, and this time you get that. Okay? So you can use it for continuous random variables, you can use it for discrete random variables, either way. And this was all written by William and Mary Folks. Undergrads, master's students, and PhD students all had a hand in that. And those were all the names that you saw on the first slide. All right, we're now going to go to one of the 4 applications that I'm going to do. And the first of those applications is a stochastic activity network. And here's the idea. These come up in something called project management. Now there's a subtle difference between project management and production management. In production management, you might be producing desks like this one. You might be producing clocks. In other words, you're doing something over and over and over, production management. In project management, you're doing something just once. So you might be building William and Mary Hall, and it's only produced once. And what you do when you're doing a project is typically you lay out what is called a precedence diagram, and that's what this is. So there are a bunch of tasks, and over here on the far left, this is when the project starts. And once this fires, these activities begin. And these Y's here represent the random duration of those activities. So obviously if it's involving a building like William and Mary Hall, somewhere along here is pouring the foundation, right? And then somewhere at the far end, you would have a much bigger network than this, is going to be painting the walls, and then you're done, okay? What the precedence diagram does is it says that this activity right here, which is taking you from node 4 to node 6, that activity cannot begin until both this activity and that activity have completed. Does that make sense? Okay, so that's a precedence diagram used in project management. Our goal here, and it's down here at the bottom, is to find the distribution of T6, and the 6 is a subscript is because we're looking at node 6, and that's the time to complete the whole network. Now there's 3 different techniques out there that are used. The first is called CPM, which stands for critical path method. That would be used if all of these were fixed constants. But you know they're not fixed constant. You don't know exactly how long it takes to paint the walls, right? That might take a little longer, a little shorter. And particularly these early things are done outdoors. You could have rain delays or like today's snow delays, right? Due to the weather. So CPM, critical path method, hits for deterministic activities. PERT is called the Project Evaluation and Review Technique. And what PERT does is it does allow those activities to have random lifetimes, but it's got some constraints on it. Okay? The third one that's out there is you can use simulation, and that's the most general of the 3, but that's not perfect because it gives you a point estimator, and then you've got to have an interval around that point estimator, so it's not so good. So we're going to try to use the language APPLE to solve this problem. Now it turns out that series parallel networks are a class that are easy to handle, and this is taken from El Maghrabi's book. This is an example of a series parallel system, and on the next slide I'll show you why. We have 5 nodes here, and we're trying to figure out how long it takes us to get from here to here with all of these random activities taking place. And we know their distributions and we know they're independent. So this was done by Jeff Malazzi. He was an undergraduate here, and he loved recursive programming. I'll bet you 2/3 of the programs he would write would always involve recursion. I don't know why. He just loved it. But anyhow, here's what he did. He took the original network and he said, look, see these 2 up here? those two can be replaced by a single arc because what operation is being used here? Convolution, right? You're going to add up the two random variables. So convolution gets applied here. When we go from here to here, you can see these two right here also get added up, and we have convolution there. Now here's the tricky one. When we take these two arcs and we reduce them to a single arc, what's the operation there? How long does it take me to get from here to here in terms of those two arcs? Minimum? It's actually maximum, but your thinking is right. It's going to be the larger of these two, won't it? Right? Because one will get there first, and then when the other one gets there, then you've completed it, right? So here we have a maximum, and here we have a convolution, and here we have a maximum, and now we've got it down to a single random variable, and that's how long it takes to complete the network. But as I say, Jeff loved recursion, so not only did he bring it down, you guys remember when you do recursive programming, when you hit that last return, what do? You go back and say, who called me, and right, and you keep flopping back. And so what he did, coming back on those returns, is he wound up rebuilding the network. So I'm going to show you one of the side effects from that that's really kind of neat. Okay, so that's Jeff's work. And it turns out when all the arc durations are independent exponential b, where b is the rate parameter, random variables, the time to complete the network has a CDF that looks like this. So you can actually get the time to complete this network right here, if you assume all those activity durations are exponential with parameter b, you can come in here and you can say that is the CDF of the time to complete the network. Now furthermore, if it was a big, huge network, like William Mary Hall, it would still work. It's just porting up to a larger size network, okay? Because I know you guys are big data people. Okay? And there's a picture of it for b equals 2. That's how long it takes to complete the network. But it turns out that's easy, the series parallel networks. The bonus material that you get for Jeff loving recursive programming, if you assume exponential 2, we're going to actually put a number in there, arc durations, it turns out you can figure out this p of pi k, you're actually figuring out exactly what is known as the critical path. Can you guys guess what the critical path is in a network? I'll go back and have a network picture up here for you. The critical path is the path where there's no slack, right? And since these are all random variables here, that's going to change, right, from time. Each time you run this network, you're going to get a different critical path. So there's a probability that this is the critical path, there's a probability this is the critical path, and there's a probability this is the critical path, and Jeff was able to capture those exactly, and he did that through the recursive. When he came back and called them on the returns, he got those numbers. There's another thing down here, and these are called the criticalities. If you look at these numbers here, which are the paths pi 1, pi 3, etc., if you look at all of the different arcs that are along in here, there are probabilities out here. They don't add to 1, and they shouldn't. These probabilities are the probability that that particular arc lies on the critical path. So if you have a high probability here, like you do for this arc A13, you want to make sure that you don't mess up and delay on that particular arc, because there's a high probability it's going to be on the critical path. And if you slow that one down, you slow down the whole project. And of course, you can have all kinds of fines and things that contractors have to pay if they're late. So they're very concerned about these things. There are dozens of books written on this. This is project management. All right, that was the easy case. This is the hard case. And this is the simplest example that I can give you of the difficult case. Same thing we have here. This is known as the bridge network. We only have 4 nodes, but it turns out this path right here and this path right here have an arc in common, don't they? And that makes the analysis of the time to get from here to here much more difficult. So another undergraduate, his name was Matt Duggan from years ago, very, very smart guy. We worked on this problem for a while, used conditional probability to solve this network, and I'm ignoring all the details, but just showing you the result. If we assume that the durations are all uniform 0, 1 random variables on that network that I just showed you, this right here, you can work this out by hand, but it'll take you a while. That right there is the time to complete the network. Okay? So our goal was to see if we could automate the process. In other words, if somebody just input a network and input the probability distributions, could we come up with this rather than doing it by hand? And so here's a somewhat bigger network. This was the one, this may be the one that I showed you originally or something close to that. Let's assume that we have exponential 1 arc durations on all of those arcs. So let's count them. You got 1, 2, 3, 4, 5, 6, 7, 8, 9. You got 9 arcs. They all have exponential 1 arc durations. And when you put it into our algorithm, this is the CDF of the time to complete the network. And that's shown on the next page. Here is that CDF. You'd never want to do this by hand. And then finally, if you find out what the expected value of T6 is, it is 4213 divided by 864 exactly. So that's the mean time